Um, I was a grad student here about a decade ago, and I worked a lot with Armin Rest, who taught me photometry, and Stefano Casutano, who taught me calibration. And in like my last year of being in grad school, Space Telescope installed security, so you couldn't just kind of walk upstairs anymore like I used to do. And so you had to kind of call up, and then it took all this time. It was kind of the early days. So allegedly, what I did was I would kind of drift behind people that did have security, which worked for some time, and then security caught me and escorted me out of the building, and I have not been back since. So this is my first time being back since I was thrown out, allegedly, and it's a pleasure to be back here. So I'd like to talk about kind of a number of things that have changed and what hasn't changed in the last decade or so. Okay, so my outline is I'm going to talk first about Type 1a supernovae as kind of the grand motivation for why some of these calibration things are so important. It's not the only reason, just the reason that I'm mostly focused on. So we talk about kind of when measurements are extremely sensitive to calibration and when they aren't. And then I'm going to talk about where we've made a lot of progress in calibration and where we haven't. Okay. All right. So quickly, as just a primer of Type 1a supernovae, we find supernovae with image subtraction. You can see it before and after. I'm not really sure where I should be pointing. We then measure the supernovae over time. We call that a light curve. And then from the light curve, we standardize it. We measure its peak brightness, its width, its color. To get a distance, we measure a redshift. And from the distance and the redshift, we get a Hubble diagram. And the whole cosmological signal is just looking to see how do those distances change with redshift. And you compare them against cosmological models. Here you could see like a model where you only have accelerated expansion or only dark energy, only matter. And the better you could constrain your distances, the better than you could constrain your models. So where calibration is going to kick in is that you need to make sure as you're measuring things further and further away at different redshifts, going into different filters, those measurements are accurate. Okay, so for the Hubble constant, though, what you're doing is you're really just measuring this first part of the Hubble diagram. So just kind of at low redshift, you're looking at the local expansion rate of the universe. Okay, so what I want to talk about is two different types of measurements. One is measuring dark energy, and one is measuring the Hubble constant. Both are part of all this like exciting stuff these days. So for measuring dark energy, what you're really doing is you're comparing supernovae at low redshift to supernovae at high redshift. To measure the equation of state parameter W, you're really looking at for signals, hey Susanna, on the about 0.02 mag scale across a change in redshift of 1. So big redshift scale and small signal. For the Hubble constant, really what you're doing is you're just comparing in a distance ladder supernovae that are at like 0.005 to supernovae that are 0.05. So supernovae that are like here to supernovae like here. And the Hubble tension, this thing that's kind of been really exciting lately, it's like a 0.2 mag scale. So W, you have to look over a huge redshift range, and the signal is really small. H naught, you only have to look at a small redshift range, and the signal is really big. So W is about 100 times harder than H naught. Okay, now what makes W especially hard is that as you're looking at supernovae across a redshift range, the spectrum of a Type 1a supernova is going to redshift. So that means where the spectrum peaks at z of 0 is obviously different than where it peaks at z of 0.8, which means that the filters that you're focused on, kind of where your signal is in, is going to be different between z of 0 and z of 0.8, or where your leverage is coming from. So you need to then understand very well your photometric system of kind of how do you calibrate your bluer filters compared to your redder filters. So you need to have this cross wavelength calibration known to this very small level. because the dark energy measurement is across as big of a redshift range as you can use. The bigger, the more leverage you have. Okay, now what's gotten kind of very exciting on the on the W side is that there have been multiple analyses. There's kind of last, I call it last generation of analyses, and they are all measuring a kind of hit. I call it like a hint of a non-cosmological constant. So this is a parameter space of WA W naught. Lambda CDM is here at where W naught is -1. WA is 0. WA is the evolution of the dark energy parameter. And you're seeing that kind of these different analyses, whether it's Pantheon Plus, Union 3, DSY5, when combined with DESI, which also kind of has its own pull in this same direction, they're all pulling to a non-zero WA. So it's this kind of very exciting time of, is this real or not? Or is this a systematic? And if it's a systematic, the kind of number one thing we want to look at is calibration. Okay, so to kind of give a scale of it, the size of this signal from kind of the middle of here to here is about a 0.04 mag shift across the redshift range of about a delta Z of 1 or so. For supernovae, you essentially kind of multiply all your brightnesses, your problems by 3, because there's a color term. So think of like RV of 3.1 or so. So if the scale of the signal is 0.04 mag, really kind of where there could be problems is about on the 0.01 to 0.015 mag scale. So you're talking about across your wavelength range or across your redshift range, a 0.015 mag scale could cause this difference. So that's really hard. And I think why people are not ready to totally jump on this is that that is a very difficult proposition. Okay, so are these kinds of problems in our data? Well, yeah. So this is showing kind of a number of the recent cosmology analyses, and how we kind of show this often is like the effect of a systematic minus your nominal. So a number of these are the impact of systematics. Here this is millimags, basically it goes up to 30. Here this is mag, so it's changing a little bit. But you can see that if you change, let me just focus on this one, if you're seeing my cursor, that's the HST calibration kind of, if the HST cal spec stars were correct. And you could get a jump up to about 0.01 mag due to kind of the stated uncertainty in the HST cal spec standards. So there's actually a number of systematics all related to calibration that are kind of bumping up at the 0.01 mag scale. Now remember, for this signal, this is basically saying you just need kind of one thing at the 0.015 mag scale, but if you had 3 at the 3/4 of 1% scale, that would do it too. So calibration problems at the kind of 6-7 millimag scale, if you had a few of them, that could cause this dark energy signal. So that's kind of very scary. It means kind of we have to work really hard. It also comes in a different way in that if you have calibration problems, you have to retrain your model. We call this the SALT2 model. This can then change your distances with redshift. This is a nice plot in Brown et al. This signal is kind of very close to the WA signal. So just by retraining your model based on calibration differences, you could kind of move those dark energy contours around. So this is quite challenging. All right. Now, for H0, it's actually a very different story. This kind of gets confused sometimes. So for H0, the idea is that it's a distance ladder, and you have Cepheids or supernovae, or you could do TRGB and supernovae in multiple rungs. And the kind of like coolness or beauty of the distance ladder is that by having these things in 2 rungs, then there's a kind of self-mitigation of systematics. So what can happen is, let's say that your supernovae, someone just totally screwed up all your supernova measurements by like 1 billion magnitudes. If as long as you make the same mistake in your second rung of supernovae and your third rung of supernovae, that 1 billion magnitude mistake just cancels out. So there's a built-in mitigation here, so that any consistent calibration error between rungs, whether it's the supernovae or the Cepheids, cancels out. That's something that W does not have. You're basically sensitive to everything with W. So for H naught, the story here is the Hubble tension, where we get it's 5 sigma locally compared to like a CMB value. And a question is, well, can calibration affect things? And so I see this great Chris Stubbs here. So Stubbs had this grad student, Sasha Brownsberger, and we kind of had this idea of let's say that you just didn't know about calibration. You didn't know how to do calibration. So every survey kind of can mess up on its own. Well, if you do that, the data is constraining enough, and you have this cancellation between rungs that even if you kind of said you don't know anything about calibration, this would only kind of affect your H naught at the 0.2 scale, which is much smaller than the delta H naught of 7 that makes the Hubble tension. So it's just a very different type of measurement, where for H naught you have this mitigation, for W you have this extreme sensitivity. Okay, so kind of motivation takeaway kind of number one is that measuring dark energy is just extremely sensitive to calibration, and the kind of the excitement where we're at now of, do we see an evolving equation of state? You could totally write in every proposal, like, you need to do this calibration thing to help with this. And I'd say kind of where we are at now is we're still, I think, struggling with 0.01 mag problems, and the next generation has to get to 0.001 mag, which just seems extremely hard, and measuring H naught is easier. Okay, so now let me talk about kind of where we've made a lot of progress, kind of since I got kicked out of here 10 years ago, and where we haven't. All right, so some of this was talked about yesterday, but I want to kind of give my own exact definitions of relative versus absolute calibration. So for absolute, I think of it as how close the number of counts per second to some real physical value. That's what I mean by absolute. For relative, you could break that into two different parts. There's like the spatial temporal. So if you have the same exact star, it's observed at different parts of the focal plane, different parts of the sky, on different seasons, different times. How consistent would that be? But then there's another type of relative, which is how accurate are the filter systems, the throughput across your wavelength range, and how is that tied to observations? So for kind of these two, they matter a lot. For absolute, it only matters in the sense of you need to be consistent with tying to other things, and I'll talk about that. Okay, so for calibration, now that we're kind of already having problems of the 10 millimeg scale, we're essentially kind of at a state where every single calibration problem matters. Like back 10 years ago, it wasn't like this. You could kind of prioritize, this was important, this was not important. Now it's just like any problem you could think of matters. Like everything that affects you on a few millimegs, it's all a problem. So spatial uniformity, field-dependent bandpass effects, temporal photometric stability, persistence, relative flux across filters, nonlinearity, lab characterization, cross-survey photometric calibration, understanding PSF issues. Like each one of them is a thesis worth of work to get to the 5 millimeg or so scale. Kind of in the future, we need to get to the 1 millimeg scale. Like I feel like we underestimate just kind of how hard the work is in front of us. Okay, but so the kind of common path for calibrating these large surveys is that you first measure the throughput of your filters. For some fields, you start like with some arbitrary tie to some photometric system, kind of knowing that, hey, that's probably wrong. Then you do some kind of tying together of all your photometric observations. I'll talk about that in a second. So you try to get internally all the stars tied together. Then with this full sky calibration, you then compare to some kind of spectrophotometric standards to set a 0 point across your sky. You could then compare that to the synthetic prediction of what that should be using your known filters that you measured in step 1. You find the offsets, you correct the full sky for those offsets, and you're done. So it's like you have to make your whole sky, your whole stellar catalog consistent. You then compare to some standards. You correct by that difference. You apply. You're done. Okay. So there's kind of three then steps. And I want to kind of say, give like green light, red light, blue light for kind of where we are for each of them. So there's tying large areas together internally. Then there's tying to all the external spectrophotometric standards. And then there's tying your survey to other people's survey. And kind of each of these has its own challenges. Okay, so for full-scale calibration, I think you're going to hear a lot more about this from Eli right after me. So I'm going to just talk about this quickly. So there's multiple methods, and essentially what you're doing is you're stitching together all your observations across the sky. And what helps is that oftentimes you have overlap between these observations. So there's kind of what's called the UberCal method. This was done for SDSS and Pan-STARRS. This is a great figure where Pan-STARRS is compared to SDSS, and you're seeing kind of the residual in stripes because of SDSS calibration problems. But kind of you could just put this into one big linear algebra matrix and kind of solve for everything simultaneously. What Eli and Dave Burke developed is something called forward global calibration method. We're kind of doing this forward, and what's kind of really neat about this approach is that you are kind of with forward modeling determining the full atmospheric and instrumental pass bands. So kind of you're understanding the impact of the atmosphere for each observation and correcting for that. So it's like another step up. And you can see again, so these are the residuals here between Gaia and DES, and kind of really pushing to, it seems like kind of like the 5-ish millimag level, if not better. Here the sigma is 0.0066. So I kind of, and maybe Eli would say something differently, but I say this feels kind of green to me. Of you have lots of data, you are stitching together a number of observations, and it's kind of like a well-constrained problem, at least at the level that we need to be at right now. Okay, so for kind of part two, there is tying to external spectrophotometric standards. So this was talked about some yesterday. So that kind of like the main catalog has been the CalSpec standards. I see Ralph here. This kind of has been kind of stated to be at about like a 5 millimag uncertainty per 7,000 angstroms. But there are the kind of the concerns are that you have uncertainty in the white dwarf standards, both kind of on the measurement side, but also in the modeling side. And what's hard about this is that if, I don't know, Ralph kind of gives us a new set of CalSpec standards, we just take it. There's nothing we could do to kind of say, you're right or you're wrong. It's just, we on the supernova side, we just put them in and all of our numbers change, right? There's no kind of mitigation at all in there. Okay, so what then happens is kind of things improve over time. So this is a nice plot in David Rubin's last paper, and showing changes in the flux versus wavelength of the CalSpec standards. And you could see that kind of these changes are on the level of about, I don't know, 1% or so. And this is the level that we already need to be at for measuring our dark energy signals. So kind of when there's a change, all of our dark energy constraints just change, and that's that. So it's kind of like we're already kind of hitting the issue of how much you could depend on the modeling of these. The other problem is that the CalSpec standards are really bright. So most of them are like 12th, 14th magnitude or so, whereas the supernovae are like 22nd magnitude. So we try to do in our surveys very short exposure so you don't saturate for the CalSpec standards. And then you kind of hope or pray or analyze that you don't have nonlinearity to go that difference from 14th to 22nd magnitude. But there's a lot of room for problems, especially kind of for those bright standards. You get like brighter, fatter effects and other things that you need to be nervous about. So you want more standards, and you want them kind of fainter. So there is this network. So just talking to Avi about this. So there's this new white dwarf network, and so this is something Avi Saha led. There's nice papers by Narayan et al., Axelrod et al., where at least kind of two of those problems seem solved. One is kind of you're getting fainter white dwarfs, and the second is
you're just getting more white dwarfs.
The main question I want to ask the group, and I just asked Sabi, is like, why has the adoption of this network kind of been slow? So it seems like kind of like as a community, we should start kind of moving towards this, because this at least gets you closer to kind of where your science observations are. I kind of just want to leave that open. Like I think kind of one thing that's happening, you can see it in the paper, is that when they will then try to calibrate other surveys and find kind of big issues with Gaia or DES or pan-stars, and those issues may not kind of be seen in those surveys. So I think there needs to be some kind of more global thing of combining this new white dwarf network and comparing it to the older CalSpec network, and then comparing that internally to your own observations to kind of make sure that everything's on the up and up. Like I do want to just say, like, hey, the problems of more and fainter seem to be solved, and kind of maybe we should be moving. Okay, so the other way of doing this is with kind of what's called lab-based metrology. So this is something that Stubbs, Tomry, a number of people have worked on, where you try kind of calibrating your standards kind of from your instrument itself, rather than kind of saying all the truth comes from the sky. So it's kind of like reversing the direction. So you're using the kind of known throughput of your telescope and some tunable laser, and you're trying to then understand it. You also kind of then need to understand your atmosphere very well, and this gets hard. But there's kind of been a lot of work on this. 3 minutes, okay. So there's this Stardust project, there's the Scala project, where kind of you're trying to use your instrument to calibrate. I'd say kind of I haven't seen that this gets to like the level that the CalSpec kind of level gets to. It's been really hard. Okay, so I kind of give this like a yellow. Feels like there's clear work that is being done, but like the focus has been good. Okay, so the kind of third thing is tying to other surveys. So let's say you have one survey really good. Can you calibrate to another survey? This kind of is a challenging problem because every survey has its own filters with its own systems, its own documentation, and it just kind of has become like this bookkeeping nightmare. So this is the thing I worked on first 10 years ago with Stefano Casartano. And the idea was to use pan-stars as the middleman and say, okay, pan-stars tells you the photometry of all the stars in the northern hemisphere across all the sky. So let's cross-calibrate to every survey. So it used to be done like this survey to this survey. Now let's just kind of do everything all at once. So you compare like filter to filter. So this is pan-stars minus this SDSS. You then compare that to some spectrophotometric library, and you look for an offset. And you're looking for those offsets for every filter combination between pan-stars and some other surveys filter. So what you ultimately get is you say, okay, for all these different filters, here's the offsets that you need to correct for. Here's kind of how much every system and every filter has messed up by. And this has kind of really advanced a lot since I worked on it 10 years ago. So this is a nice paper. This is a paper by David Rubin, where you could just see these like tables upon tables of saying, all right, I'm going to kind of use pan-stars and recalibrate every kind of single system and every single filter and different periods of every system or survey also. But like, it's becoming a huge amount. This is kind of another one by Brout, where it's trying to make a covariance matrix. So here's, you can't even see it, but it's every filter crossed with every filter to understand the covariance, and then retraining that SALT model that I talked about. But like, as more surveys come online, this has just gotten more and more difficult. So, I'll also shout out. So there's a poster I think I see here by Darcy, a paper by Brody Popovic and Darcy Kenworthy on this. But I think like what's just so hard about this is just the amount of documentation that's getting to be needed for this, and bookkeeping has just gotten extreme. Okay, so I kind of call this like a yellow, but I'd say this is like actually getting worse. Okay, I have 2 slides. It's getting worse just because as we have more surveys and we're trying to keep on pushing down just to to smaller levels, it's just getting harder. So say kind of one thing of optimism, one thing not. So we can compare lots of things and kind of root end things down to get things better. But at the millimag level, it's just kind of getting harder and harder to track multiple things at once. And I think that my kind of takeaway number 2, and I'll leave it here, is that it feels like we're at this crossroads. Either we kind of do these projects like kind of what I just talked about, where you're including lots of different samples, but you need to track now 30 samples at the 5 millimag level, or we just kind of say screw it and we just move on to LSST and Roman or something. And I kind of don't know which way you're going, but I think we need to figure it out. My second thing is just that there's all these kind of different pieces of the puzzles tied to standards, relative calibration, cross-survey calibration. I think there needs to be like a pipeline of calibration that could kind of do it all that people can plug into. This exists for every cosmology community, some kind of pipeline, but like this doesn't really exist for calibration, and I think it needs to. So I'll leave it there. I'm happy to take any questions.
Questions?
So I guess on the Ralph Bolin cal spec, it seems like your argument against it is that it changed because he updated it. Why not just say, well, the latest update is the best and not so much worry about the sociological history of the matter?
Well, yeah, changes are often good. Like I change my stuff all the time. It's just that the bigger problem is that we can't cross-check anything. So if Ralph updates something, then like this happened, we were doing our last analysis, like we found out a few weeks before we're about to submit our analysis, we just have to change everything. So it's not that updates are bad. I definitely don't want to say that. It's that we have no way of giving our own stuff to the problem. It's just we eat it. It's a one-way problem. We eat it and then change. So there's no cross-check.
So JWST is finding supernovae at redshifts of like 7.
Yeah.
I don't think the cadence is good enough to help you much, but presumably that could be fixed. Are there special calibration steps that need to be taken that would be
right? So yeah, so there you're then calibrating. I mean, there the light is super red, so that's even. I mean, this is like Z of 0.8. And so you're kind of much deeper into the infrared. I do not know how well that can be calibrated. I think for those studies, it's very interesting of like, do supernovae still look the same? Like they have the same kinds of features, but to use that for cosmology, I think would be really hard. It would be interesting, but yeah, I don't know if you could kind of calibrate things to the 5% level, but it's a really interesting problem.
Well, it was a question, not a request for your opinion.
So the question is what can it be done?
What should we do? What would it require?
Oh, so I mean, it's the normal thing. If you could have some kind of model that you think you understand in the infrared, then you could do the normal calibration. So you're tying to a white dwarf model, and you go from there. So it's just how well can you understand your white dwarf model all the way deep into the infrared.
It's a question of measurement. Deep in the infrared, where the red objects come up and the white dwarfs get really, really faint.
Yeah.
I will say we are calibrating the white dwarf models.
You into the far infrared.
Far infrared in your mind is.
I mean, like, sorry, and like a Z, whatever Z of 8, a Z of 7 would be in this hypothetical case. So let's say.
Give me a wavelength.
So 8 times 40,000 angstroms.
4 microns.
4 microns.
Absolutely.
Okay. So okay, fine. Okay. So then it's doable then.
That's still near infrared in my book. Okay, near infrared. And 1%.
Oh, okay, that's great. Yes.
I think this would be a good discussion for the coffee break. There might be something interesting here.
Yeah.
We have a little time.
Yeah, so we can take a couple more questions. Sure.
Just to reply to your question of why we haven't adopted RB's white dwarf network, we did consider it for Euclid, but the reason we didn't in the end use it was because our continuous viewing zone is just about 2.5 degrees around the ecliptic poles, and we wanted for our performance verification and something, and the launch data uncertainties and our restrictions that we have in planning. We needed something in that continuous viewing zone.
So was there a CalSpec standard in that zone?
No, there wasn't.
Oh, so what did you choose?
We searched our own white dwarf candidates and confirmed them and observed them with HST. And I think Susanna said they covered
The microphone.
part of the CalSpec.
Yeah, no, here over.
So he's saying, so for Euclid, the reason they didn't use the Saha standards is that they have a continuous viewing zone and there are none of those standards in that zone. But there weren't CalSpec standards either, so they kind of made their own standards.
I do my talk, I'm going to elaborate a little bit on what the caveats are. And resolving small differences we have with CalSpec. But I think we have time for another question.
Oh, thank you. Can you just say quickly how numerous, widely distributed, and bright the Axelrod white dwarfs are?
Yes. Will you answer that?
I can show you a graph. It's in my talk for
Okay.
Friday, but I'm happy to show it to you offline. There are 35, including Ralph's 3.
Okay.
Okay, thank you.
Seeing any hands?
Thank you, everybody.
Thank you. Yeah. Speaker is Eli Rakoff.
Hello? I think this is on? Yeah. I don't know what to do here.
Getting anything?
I have it on.
Look at this. See,
No, you're- Oh, what? Ah, yeah.
and then you just have to click before you take that thing.
Uh-huh.
Move to single page, or else it'll be messed up.
Some combination of mode and that little arrow.
Okay.
But hang on a second.
Does he notice this? Hit them on it.
All right. Hi there. I'm Eli Rykoff. Come to here to talk about, excuse me, Rubin calibration. After hearing the other talks, I wish I had written a different talk. This did not
Eli,
go correctly.
you have to click that thumbnail thing again. It didn't work.
Hold on. It says single page.
That should work.
It's not displaying properly.
Yeah. Shoot. Hold on.
I do my screen.
Yeah. What?
Wait, that Chucksman knows how to fix this.
And-
So this is giving me two.
Yeah, I know. I don't know what to do.
Consistent.
This is my special. What if I did 2 pages?
No.
No, that didn't work.
Now go back and maybe it'll improve in it. Never know.
Yeah.
Okay, now.
Okay.
All right, full face.
Crossed.
Nope. This is
Do slideshow instead of.
Oh yeah, try slideshow.
Here we go.
slideshow used to automatically advance, and I didn't. It was if it starts playing, I apologize.
You have to speed up.
What? Is it?
No, it's not.
Okay. So, Right. Hello. So, as Dan introduced a ton of wonderful stuff, we're trying to get to millimag, and I don't know how to get there. But photometric calibration in 3 easy steps. You remove all your instrument signatures, you combine all your measurements, and you apply it to all your objects in the survey, and it's really easy. And Dan introduced this as well, and we've discussing the difference between the relative calibration and the absolute calibration. I worry a lot about the relative calibration with large surveys. We're going to have 20,000 square degrees with LSST. And the stability, repeatability, if you return to the same object, you get the same calibrated top of the atmosphere flux. Let's ignore the galaxy for the moment. Uniformity, if you go to different parts of the survey and look at a star with the same SED and distance, do you get the same calibrated flux? And we care about stars and galaxies across a wide range of colors, not just white dwarf SEDs, of course. And something that I don't really address here, but I want to bring up the real pain in the butt that red stars tend to be fainter. And so there's a degeneracy between getting your bright, faint linearity corrections and your color part correct, and you can make everything look, you can mix those up quite easily. And all of our white dwarfs are blue. Chromatic uniformity, if you compare stars of different colors, do you get a consistent ADU to flux transfer? And then the absolute calibration, separately, 5 absolute color terms for a U-Grizzly survey. As Dan introduced, it's very important for supernova 1A. And then 1 overall absolute term to transfer to true nanojanskis or something like that. And it's kind of hard to find a science case where that is essential, as Chris Stubbs was talking about. But we need to think about all the cross-survey calibration, different wavelengths. So understanding your passband is extremely important. And so for all of these things, I'm going to go back a little bit to the instrument signature removal, because if you don't get that right, then you are you're sunk. We have kind of a complicated readout chain that we've modeled together for the LSST camera. I can discuss this in greater detail, but one of the fun things, the ASIC chip is called the ASPIC. It's named after the ASPIC Viper. You might hear about that more in the future. But we've got various sources of crosstalk and linearity, and we just have a whole instrument signature removal to take care of all of this, because we have 16 different amplifiers, all with different gains. And there is the gains can vary with readout board temperature. Fortunately, we've gotten a lot better control over that temperature before the camera goes on sky. So shouldn't have equations, but here's my one. The computing the calibrated flux to get from A to U up to, or to get, from what hits the top of the atmosphere to A to U, depends on the source SED, and this is an integral from 0 to infinity, as if there's any out of band light, but really this is an integral over just what is within your passband, the observed band, which varies as a function of position over the detector, over the focal plane, over alt and as because of the atmosphere, over time, over wavelength, all these terms that we have to figure out. And then the source SED within that passband. And so the wider the passband, the more difficult this is. Also, reddening effects are more difficult, so narrower passbands are easier in that way. But of course, building a big filter with narrow passbands is also a challenge. But we have to calibrate, we have to understand that observed passband. And what we always talk about first is worry about the atmosphere. The first thing we do is choose our standard atmosphere to be as close to the typical conditions as possible to minimize the corrections that we have to do. Choose a good pivot point. And here's our components. This is from ModTran. There's oxygen, ozone, Rayleigh scattering, aerosol term, water vapor in the red, and then all combined. And so what this does, these are the nominal LSST filters, and you add the mirror lenses, the detectors, the atmosphere, and you lose a lot. And the U band there in the corner being a pain in our side. But one of the fun things to look at in particular is the Z band. Here's the filter in the instrument, and here's with a little bit of water, and here's with a lot of water, and you can overlay them, and the water vapor takes out only the reddest end of the Z band. And so the effect of the water vapor, if you have higher water vapor, it decreases the amount of flux on your detector, but at the same time, it has a chromatic effect. So objects with different SEDs have a different effect from the water vapor. And the primary change is the transparency. But to predict the total throughput at the millimag level, we need to know the water vapor at the 0.2 millimeters level. But this is degenerate with any gray or opacity measurements or aperture effects. I have a short time, so if anyone wants to talk about aperture corrections. But the secondary impact is this chromatic effect. And mostly the red end is removed, and the size depends on the SED. And so here is the impact on the I-Z color. And this is a range of stellar SEDs in red and a range of supernova SEDs over a wide range of redshift. And so if we know the water vapor at the 1 millimeter level, then we can really understand at the millimag level what's going on in the Z band. The Y band is harder because more of the Y band is chunked out, except at the blue end of the Y. This, I'll get back to this in a moment, that this has a measurable effect. So how do we model this atmosphere when we're observing? We have the auxiliary telescope to observe stars around the sky, very bright stars with low resolution grating, or the quad notch. I'll say a little bit about that. And the primary method that we're using is self-calibration, the descendant of UberCal via the FGCM. And this is solving the global calibration problem with a physical model of the atmosphere and instrument. FGCM works, any variation in the atmosphere that has an observable effect has an observable effect, and that's the key to the self-calibration. And the atmosphere is actually there's not too many parameters, as I showed. It's not super complex, and so there's enough information from the photometric observations to really constrain what the atmosphere is doing quite well, as long as you have a network of observations in different bands over the nights. There's additional complications that when the moon is up, we're going to be observing in the red end and the red bands, and when the moon is down, the blue bands. It would be nice to have a space telescope, and then we avoid the atmosphere entirely, but we don't. And once we know the atmosphere, we can predict fluxes of all the objects in an exposure. Everything is physically motivated. It uses a full range of star colors, fits instrumental transmission variations. We can look at evolution in the degradation of the mirror reflectance. I can talk more about that if anyone asks me questions. I have additional slides. So I probably should hurry up to get to some fun things. Going back to the water vapor, one of the things we did with the dark energy survey is we can model the water vapor directly from colors per exposure. So you take a Z band exposure. We've got a big 61 detectors. It's smaller focal plane than LSST. And you basically look at how the reddish stars are changing compared to their standard magnitudes, and the bluish stars, and the gray term all cancels out, and you get a signal, and you can measure the water vapor on a per exposure basis. This is not actually what goes into our model. This is just a check, but it does work pretty well in constraining the water vapor, and it should be even easier with LSST with a larger focal plane, as long as we assume that the water vapor is not changing over that small spatial scale. At the same time, we have the Oxtel. This is a 1.2 meter telescope on Calibration Hill. It's got a low resolution disperser to measure PWV at the red end, and the quad notch filter from Chris Stubbs et al. And this is SK's little figure. 4 simultaneous bands to measure aerosol optical depth. And this can be looking at stars and tracking at the same time as the main telescope. The exact survey strategy is TBD, and we're going to be using this basically to validate FGCM in the first year. But that's the atmosphere. The instrument is actually much, much harder. And we've had lots of things. You're looking at all of the residuals on Hubble with space and per amplifier and the L flat and all of the fun things. You can't go backwards. You can use those photometric observations to measure what the atmosphere is doing. Simple number of components, as long as we trust our atmosphere models. But for the instrument, there's too many degeneracies to go backwards. So if you see a chromatic shift, is it due to the red end or the blue end of the filter being off? Is it due to the AR coding causing a different throughput shape? So we need scans. We need to know the QE of each detector, at least sub-detector. Even better is a function of wavelength, the variation of the filter. The mirror reflectivity is a function of wavelength and time. In DES, we use the DCAM calibration system, or DCAL, not to be confused with the DCAL survey. This came before. It's full system throughput with a monochromator. And we've got a laser for LSST to track the same thing. But I'll show the collimated beam projector in a moment. But the impact of the atmosphere, at least in the G band, the instrumental variations are larger, but at least they're static. This is in DES on the left. This is the impact of the different AR codings and the different quantum efficiency as a function of wavelength for each detector. And you can see it's this is in millimags. It's it's a 4% effect depending on what detector you're looking at. And this is you really get from scans on the right is what it's going to look like for LSST. We have 2 types of detectors, E2V and ITL, and within each family there's variations in the AR coding, but they also have different throughputs. And I should show what these look like over each other. I cut that slide out, I'm sorry, but the impact is kind of a 2.5% effect. And again, there's no substitute for scans. For the filters, we have vendor scans of the filters, and this is the R filter, and this is a kind of a 1% effect over the focal plane, and this is because of the red edge of the R filter does vary a little bit as a position. For flat field scans, we have a tunable laser and a flat field screen for in situ scans. I should have updated this, did not get installed in September. Soon, we can scan with wavelength, but the even better thing is the collimated beam projector, and Alana is here somewhere. Ask her about the CBP. We have a fiber spectrograph to monitor the output wavelength, the electrometer to measure the light level. And the CBP was damaged in shipment, but is ready to go back up the mountain, I think, next week. And it's basically a telescope in reverse. It gives you a collimated beam out. You can only put it on a small bit of the mirror, we can scan it around. I'm gonna, and we can test the throughput measurements, measure illumination corrections, and this is what it looks like for HSC. These are, this is the star flat, the effect. This is the residual after dome flat fielding for focused light. We can fit all this out. And then in the end, this is an update from what Dan showed. This is the DES 6-year calibration uniformity compared to Gaia, synthesizing Gaia G-band from GRIZ. It's better than 2 millimag uniformity. And the residuals we see, except in the corner, which I don't understand, it's some systematic due to background light from blue stars, I think, is Gaia scan patterns. So they're still better that we can all do. And I have 100 more slides or pictures of cross-survey calibrations, not in this talk. So thank you.
Suzanne, pass the mic, please.
So in all your discussion of the atmosphere, you never mentioned clouds.
Yes.
And presumably you're assuming that it's completely gray because that's a normal assumption. But
yeah.
First of all, how well do we know that that's the case? And secondly, even if it's gray, there's going to be a whole bunch of essentially fractal variations with small changes in position on the sky. How do you deal with that?
Okay. So that is a great question. I kind of skipped over the cloud part. So there's two parts to this. Yes, I have assumed that they're gray, and I haven't seen anything other than that. In the fit for everything that we do, we reject all observations that are not consistent with the model that basically have cloud extinction. And in DS survey, that's actually 80%. Most of the variations that we see, when it's cloudy, we're not observing. And the marginal amount of clouds is not a ton of observing time. And those just get fit later, but they do have increased noise because of the fractal nature. There's not enough stars to actually constrain the spatial variations at the millimag. There literally are not enough stars in the galaxy in order to do that. So you have to eat the errors for that fraction of observations that are affected by clouds. But otherwise, it seems for the DS, it was very smooth otherwise.
You have a question online.
Oh.
You postponed talking, this is from Ariane, you postponed talking about aperture corrections. What would be your main message there?
Okay, aperture corrections are a pain in the butt. One of the, especially when we get down to, towards the millimag level, and this is something that was in Bernstein, one of the 2018 papers, at the few millimag level, variations that we see that have been in the past described to variations in transparency are actually variations in the amount of flux that's coming in whatever aperture you chose. You want to choose a large aperture, and then you have to worry about backgrounds and all this. But the wings of the PSF vary, and the light goes in and out of that, and so you have to control that, and that is at the 0.5% to percent or even more level. And it does not seem to be clouds or variations in that. It's something in the atmosphere that's scattering stuff in and out. And we had talks yesterday about they go out to infinity, and you choose some aperture and things change, and that is absolutely one of the limitations in getting down to the millimag. And I don't know a way around it at the moment. I don't have an answer. We can improve on it, but we can't fix it.
You mentioned dome flats. Could you say a little bit about what the screen is and what the illumination source is?
Okay. For the dome flats for LSST, Flat fielding is a whole other talk of pain. But what we have is either the tunable laser or LEDs, which get projected onto there's a little reflector that's mounted on the back of the camera. And then it goes, the dome screen is a big donut torus that covers the whole focal plane. So we've got various LEDs or the tunable laser, which goes from 300 to 1100, that we can illuminate with that. But what to do with the flat field is a different question, because you have to worry about what we're tracking there is generally pixel area variations, and if you don't do it right, then you end up either messing up your aperture or your model PSF photometry. So that has to be done carefully. That's another talk.
I just wanted to add, I have measured Vega through 6 to 10 magnitudes of clouds. It's almost gray. There's just a little roll off in the red, as you'd expect. So anytime you're observing, I think you're going to be fine, assuming it's gray.
Thank you. Okay. There, an answer that yes, gray.
Question.
Yeah.
You talked about the water vapor absorption, but water vapor becomes kind of optically thick, so it doesn't behave it doesn't scale with your air mass anymore.
We trust ModTran to do it, but there's the other thing that I learned along this, which is obvious in retrospect. Why was something, in a DS we have up to like 13 millimeters of water vapor, and I'm doing HSC modeling, and ModTran was crapping out. What? Because at that altitude above 3 millimeters, it's a cloud. It's totally saturated, so that's why it's dry. It's either dry or cloudy when you're on top of Mauna Kea. There's just not enough capacity in the atmosphere above it to hold that much water vapor. Yeah.
Any questions?
Yeah.
Thank Eli again.
Albert?
Right there.
Yeah, there we go. Slideshow. So now for something almost completely different. So,
Not again.
oh no, how did we get? So it's going to the two.
Slideshow.
Oh, slideshow. Okay.
Technology is so wonderful.
There we go.
And also use the clicker.
Excellent. So, yeah, back. That's going to.
Slideshow, it's enter slideshow.
I did do slideshow.
Yeah, we did.
Did.
There's a menu item for singular page, which is somewhere there.
View. Oh, I see what's going on.
And
Okay. Hang on. By Thursday, we'll know how to run this.
yeah.
I think that's the idea.
Okay. All right. So I think all speakers have done an excellent job showing that this is a almost impossible problem now, getting to millimag photometry. And in the future, a very near future, it will be, not just almost impossible. Without something very, very, very different, it will be impossible. Okay, we won't be. We're hitting the limit with, and we've seen that with. We've started to see that with Type 1a supernovae and dark energy. It'd be nice if, like a lot of astronomical measurements, we didn't care so much about precision calibration. But supernovae, dark energy from Type 1a is just, it's an ever hungry and is going to be ever hungry beast, because as the statistics keep getting better, it's going to create more and more demands for better systematics. And we need something different. So what can we do? What would you want to do if you had you could do anything? What you'd want to do is calibrate surveys like you would just totally in the lab. You'd put a source right in front of the thing you're trying to calibrate, move it back and forth, and calibrate it that way. And next to your so-called standard source, you would have its own detector to put it on a detector-based standard scale, and that detector could be directly traceable to a physical source like the power device at NIST. What is the analog of that? It's putting a source above the atmosphere, for example, on a balloon. A balloon is not a replacement for a satellite, of course, because it is not above the entire atmosphere, but it is above the vast majority of it. And I posit that while we can hopefully have at least one or two satellites, calibration satellites, in the future. As Susanna mentioned, we can't be constantly putting satellites, new satellites up there. We have our green stars, but satellites themselves are not so green. But balloons are. Balloons, we can keep putting sources up there. In fact, the goal is to every dusk hand launch one of these things. Could be launched out of the back of a pickup truck, or two or three in different areas of the sky. Have them be able to move around in the sky and calibrate exactly in an observer-controlled way what we want to calibrate that night. This is the start of that, and so you choose for convenient, useful wavelengths for which laser diodes exist. At those wavelengths, at reasonable powers, and you have an integrating sphere such that your light is evenly smeared around the inside of a sphere, and then a little hole in the bottom to let the light out toward the telescope, and another little hole for each of your measurement, your onboard measurement, which are NIST calibrated photodiodes, or as I'm also Canadian, NRC calibrated as well. Smaller institute, but that's Canada's National Standards Laboratory. So what is the basic payload design? Here's an old left. You have an old view of a cylindrical device. We've moved to rectangular, and you need to be able to control this thing up in the air, control the light sources, and know where it is at any given time, and move it. What you don't see here in the solid model is the ability to have some form of propulsion. Of course, not because you want to fight the winds. You don't want to, but you do want, because you'll waste the battery immediately if you constantly fight the winds. You want to optimize this with knowledge of the winds at all relevant altitudes throughout the night. So you also can have propulsion to, when you're doing a given observation, if you need to, move the payload right in front or right in back, right around exactly, for example, a supernova for which you want to calibrate. So this is a busy slide, but how are these things all mounted together? I'll first say what all those curvy arrows are. These are laser diode modules. They're swappable, not of course in the air, but you can swap them out from one another. This company in Toronto makes very nice modules that are all the same form factor, and all can be made fiber coupled. And you can, although perhaps nominal, should be 440, 532, 658, and 830. You can swap the red ones out for even redder, the blue one out for an even bluer one, for example, and anything that a solid state physicists have managed to make a laser diode for. The heart of the measurement, as we'll talk about on the next slide, though, is the photodiode. You don't trust that laser diodes stay at the same brightness at any time. In fact, you might want to pulse them in order to, you definitely want to pulse them in order to be able, or at least turn them on and off, to be able to subtract out the background reflected light, little bits of reflected light off the balloon and off the payload itself. So we have two measurement photodiodes using two different technologies, silicon and InGaAs. And they're also mounted on the integrating sphere as shown. What you see here is actually an integrating sphere from OrcaSat in which the lasers were actually directly mounted, just single diodes instead of fiber coupled modules, directly mounted on the integrating sphere. But it's the same sphere, it's just instead of the direct mount of lasers onto the sphere, you can have a coupling of the photodiode on there. So the heart of the measurement is being able to read out the photocurrent on those photodiodes ultra precisely. So over many orders of magnitude, as many as you can get it, of brightness, because you can control using both analog and with greater range, digital pulse width modulation, the brightness of the photodiodes across 10 orders of magnitude from the analog of a magnitude 25 at dimmest up to magnitude up to 0th magnitude. So we need to be able to measure in situ the actual amount of light coming out of the laser diodes and being shined onto the telescope. And the readout module, the electronics there, it's based around a transimpedance amplifier that needs to be, of course, RF shielded, but it needs several different gain settings. And those relays You might think, why do I have these big, silly-looking rectangular relays here? Why not just use some solid-state device to switch between gain settings? Well, you can't, because if you do that, the off, what you want when turning a relay, a switch off, is to have it completely off, so there's not, so that the impedance across this, the given switch, when it's off, is petaohms. It's completely an off switch. The solid state switches don't do that. They're made of silicon. Silicon has a non-zero impedance even when it's in its disconnected off state. So you absolutely have to use a non-solid state relay, and with the relay you need to deal with things like thermal effects with the different metals when they contact one another. So you have one company in Clacton-on-Sea, England, that makes fancy relays that have a very low, incredibly low thermal coefficient that are sufficient for this. So that's the digitization is what it follows that, of course, but needs to be precise and with many as much dynamic range as possible. So here's a view of the prototype payload. And I'll move on here. So you also need to control this in the sky. So this this is the software for doing that. It's all open source. You can see it, even run it yourself. At this using the code at this GitHub site and instructions. So another possibly just as critical, perhaps even more critical thing is you don't want to get shot down. So you may remember the incident about 2 years ago with a balloon from a company, not a company, a country on the other hemisphere that sent a very large balloon drifting across North America. We don't want that. Our balloons do not have any nefarious intent, and we want to make that clear to whatever powers that be that control airspace. So fortunately, 10 years ago, this was not doable. But now a tiny little transponder that's this big is available from a company in Montana called UAVionics. A beautiful, beautiful little expensive device. So our collaborators at McGill have a nice big team of engineering students that do flights, balloon flights, and our first testing flights will be there. Of course, this has heritage from earlier work that we've done with flights in New Hampshire at Dartmouth, together with Chris Stubbs and his colleague that has retired from Dartmouth there, York Brown. But now we're at the moment all Canadian, so we need to fly in Canada, and the McGill group has the capacity to do that, and so you can see here them preparing for a test flight, an initial earlier test flight from a couple of years ago, and its predicted paths. And the equipment we have for controlling this from the ground, keeping in contact with it. So in conclusion, in principle, and we need in practice. Artificial sources can provide up to 2 orders of magnitude better photometric calibration precision. Perhaps if we get to that when we'll finally need to use the term micromagnitude, micromag, and not just millimag, then we'll perhaps need to fly, instead of just photodiodes, actually fly radiometers. But in principle and in practice, and must be in practice, that can provide 2 orders of magnitude improvement at least. And they have all these capabilities that natural sources do not. Plus, balloons have the workhorse ability to be inexpensive, launch them every night, recover them early every morning. For example, Ruben could own 3 or so, launching them at dusk each night, flying to different areas of the sky, returning home each morning. Fully observer-controlled choice of spectrum. We don't need to just use laser diodes. We could use LEDs, color, brightness, and it's not restricted to optical infrared, for example. Not for Ruben, that's obviously all that's needed, but for microwave, you can have microwave sources and have them calibrate polarimetry. And they don't replace having a satellite source such as future Landolt, which you'll hear about later on in the week. But Altair style balloons can, and I posit will, be the low-cost ground-based observatory-owned workhorses that will provide micromagnitude level calibration in the future, hopefully near term. These things even have far more use than astronomical calibration of any sort. They can you can do all sorts of things with them, but that's.
I'll just speak loudly. Okay. Is that okay? So the brightness of the source as observed by the telescope changed depending on the angle between the telescope
absolutely.
And the bore site of the opening on the integrator.
Yes. So that can be calibrated to a degree level. So what an integrating sphere gives is a Lambertian spectrum. It's pretty broad. It's not a collimated beam. So it's pretty broad, and that's good in that you don't perhaps don't need to and in practice, even for sub-millimag precision, you don't need to know the angle better than a degree. But with yaw pitch roll sensors, and you have a couple redundant little yaw pitch roll sensors on board, you can get, 1/10 of a degree, 20 times per second level precision on the orientation. And of course, with GPS, you know the position, the true position, pretty darn well.
Great, you predicted my question well. Thank you.
Okay, thanks.
Thank you very much. Very interesting project. One thing, maybe I missed it. What is the ceiling or your operating altitude?
20, yeah, sorry, I didn't mention that. 20 kilometers is the nominal, but you can go anywhere between 12 and 30 kilometers is operable, even below 12, not above 30. Yeah. So.
And how do you then return to the launch site, or
you can the nominal way would be is with a helium valve. You open up a valve and you descend. The old-fashioned way is you cut off the balloon and you just have the payload descend. But it might be nice to recover some of the helium. Recycle the balloon. So having a helium valve is a nice thing.
There's a question online from Gary Bernstein. How well is the position of the balloon controlled? and the altitude not far field for Reuben? And how fast are they moving and need to be tracked by the telescope?
Right. So the precision of the measurement of where it is to about a half a meter scale. In terms of control, that will depend on the wind and the details of exact details of future propulsion. If you have a really windy night, it might be hard to control it to a great deal of precision, but you can utilize, and there will be a complicated algorithm for utilizing the winds to, if the winds at this altitude are troublesome, then go higher or go lower, and be able to control it to somewhat close to the degree of precision that you can measure it. You wouldn't want to bother trying to control it better than that, but to a meter scale precision.
This is very interesting. Does the telescope on board the balloon, is its focus at the exit port of the integrating sphere, or is there a lens that's projecting
there's no
focus?
telescope in that, this is there's no, the only optics here, and there could be no optics, the only nominal optics is a window. So no lenses, just a window. And in fact, you can get them window free. In fact, that's actually favored, at least by missions that have used these, for example, in space. You don't necessarily want the window because there could be outgassing from the photodiode surface onto the interface of the window. But the Hamamatsu doesn't particularly like to make them without windows because A, it's trouble, and B, it's not an easy thing to handle. If you have a photodiode without a window, then it's really ultra sensitive to any little bits of dust, and so it's nice to have windows. And now they make them hermetically sealed so that even for space applications, you shouldn't need to take out that window. Yeah.
For the photodiode circuitry,
yes.
What level of precision are you getting? Are they available? And
it's still
they cost.
In terms of electronics, they're not cheap on the most little resistors off of DigiKey are 12 cents a piece. These photodiodes are a couple $100 a piece. But that's cheap, scale of a space or even near space mission, it's pretty cheap. The laser diode modules, they're of order $1,000 a piece, but that's still reasonably cheap, and they come fiber coupled, usable with a special fiber that takes all the fibers into a single fiber leading into the integrating sphere. So did I answer?
I was talking about the readout electronics.
Oh, yeah. So the goal is to get that part per million level, so that it's not an issue. Maybe a couple parts per million, et cetera. If it were in the part per thousand, anything above a part per, or anything in a part per thousand level, then it starts being a systematic uncertainty that you need to check. We want that you need to carefully deal with analysis-wise. We want it so precise that we don't have to worry about it. So if it's in the part per million level, then we won't have to worry about it. That showing that and testing. I have a graduate student working right now and testing these to test them and we have equipment to test them at part per million level. That remains to be done, but we think we can get there.
Last question.
We are 15 minutes late. Maybe we should keep going.
No, we're fine.
No.
The last question.
Okay.
It's the mouse.
No.
It's the mouse.
You got to practice. It's playing. How do I stop this? How can I stop this playing? Or is it? Okay. Okay. All right. Hello, my name is Misha Schirmer. I'm the Euclid calibration scientist. Oh, got the beep. And I'm giving this talk on behalf of the Euclid Consortium. I will not talk so much about, am I allowed to start? Okay. I'm not going to talk so much about the calibration standards we use, and I'm definitely not diving into how we calibrate Euclid, because then there won't be time for anything else. But instead, I will point out a few issues that came very unexpected to us and that affect our photometric calibration and how well we can do this. A quick overview. We want to do a 14,000 square degree survey. It's a cosmological survey employing weak lensing, galaxy clustering, and the nominal duration is 6 years. Our field of view is about half a square degree, and we tile the sky in a step and stair pattern, as you can see here on the right. This is one of our typical survey patches. That's how they look like. That's 246 square degrees, which we observed in June. And on board, we have two instruments, an optical imager that's called, we just call it VIS. That's 36 CCDs. And the nominal survey depth is 26.2 magnitudes. And we also have an infrared camera, which observes 3 photometric bands of I, J, and H down to 24.5. And we also do slitless spectroscopy in 2 bands. Here's a quick view graph of how our passbands look like. On the left, this big blue area, this is the passband of the optical camera going from 530 to 920 nanometers. The dashed line that you can see superimposed and extending more towards the blue as well. This is the Gaia passband to give you a comparison. And the 3 colored areas to the right, those are the YJH passbands we have in the imager. And the graded shade, the shaded gray areas at the bottom for comparison, these are the NIRCam filters on board James Webb. I'm going to skip over this one. We had a very simple pre-launch plan, 1 month of commissioning and then 2 months of performance verification and calibration, 2 months of PSF modeling. That sounds crazy, but we are a weak lensing survey, so we need to know the optics, the thermo-optical response of the telescope and how that translates to the PSF. And then we thought, okay, then 4 months later we start observing. Well, this is not what happened. First of all, very quickly we found out we had a massive tracking issue, so basically we started performance verification after 4 weeks. And after 2 weeks, we basically had to give it back to industry to fix the guider. And then we had to resume the performance verification, and we found stray light, we found interference from the sun, and we found molecular contamination at a later time. But these are the 3 contenders here I want to talk about during my presentation. because they all eat into our photometry budget and our data processing. Stray light, first of all, only the optical camera vis is affected. The infrared camera is not affected by this. And what happens is, on the left, you see this rendering of our spacecraft, and at the bottom, you have this boom that's protruding here, and there's another boom a little to the side, and then there's a thruster nozzle at the end, and the outermost few centimeters of that boom, they are illuminated by the sun. And that we knew. What we didn't know was that when the light from the thruster nozzle gets reflected onto the backside of the sun shield, somehow that reflected light makes it through all the layers of thermal insulation into our instrument cavity. We don't really know how that works. There's some holes, or Airbus says we knew MLI is not light tight, but they built the thing. Anyway, so the light comes into the instrument cavity, and then it hits the, sorry for the people who are remote, but I'm pointing here on the screen, and hits the vis shutter. That's, you see vis pointed out here. It's this big box, and it has a leaf shutter that opens and closes like this. And the shutter is mounted on some struts down there, which you can see on the photograph at the bottom right. And that's where the scattered light hits. And that means the light gets underneath the shutter blade. So even when the shutter is closed, we still get stray light onto the detectors. It's a really nasty problem. And it also means when the shutter is open, you get all the additional scattered light. So the shutter closed and shutter open stray light that we get is not the same. How does this look like in our data? On the left, you see an image, one of the very first images we took after we turned on the instruments, and there was just stray light everywhere. And that was crazy. To give you an idea, it's about, depending how we orient the telescope, it's about 10 to 100 times brighter than the natural sky background. That was, wow, people were pulling out their hairs. Fortunately, we figured when we rotate the spacecraft a little bit, just a few degrees, this thruster nozzle will move into the shade of the sun shield, and all the stray light disappears. So that's how we operate. Euclid is always a little moving like this. And, but we still have some residual stray light. So on what you see on the right is a dark frame, a master dark, and you see the stray light has multiple components. It's very low, but it's at a level that that we're worrying about and we need to correct for it. Okay. So the stray light is always present. It's spatially variable. It has multiple components. It depends on how Euclid is oriented in space with respect to the sun. And we need to build stray light dependent biases, dark CTI correction frames, and we need to build stray light models for the on-sky observations as well. It's complicated, but it works pretty well, as you can see here. For example, on the lower right, you see an image that we released was it last year or spring this year? I don't remember. It's of the Perseus cluster. And with background modeling, all the stray light disappears and we go down to surface brightness of 30 magnitudes per square arc second. And the image on top, we released that last week. It's a stack of one of our survey patches, 132 square degrees. And there we reach a surface brightness of 32 magnitudes per square arc second. You see all the galactic cirrus popping up. And first time I saw that, I was like, no way we're going to do cosmology here. But once you go to the actual native resolution, you don't see any of this. Euclid is an amazing low surface brightness machine. So stray light is under control. Next thing that happened, not sure this is going to work. This is a movie. Let me click on it. So that's one of our fine focus fields that we had. No, this will just move to the next slide, I think. No, sorry, it doesn't work. Yeah, well, that's not what I wanted. Okay, this is the slide I want to show you then. So basically what happens is we got these really strange patterns of cosmics. And once we put all the detectors together and binned them up, then we got what looked like a medical X-ray exposure. And actually, this is what it is. So give you an order of scale. So this is a 4K by 4K CCD, approximately. So 1 out of the 36. So that's supposed to be an image of the sky, where you see stars and stuff, but you see wires and cables and honeycomb patterns and plugs and whatnot. And this is when we have a flare on the sun. They're very X-ray bright, and some parts of our sun shield, maybe 1 in 100,000 or 1 in a million X-ray photons gets through. I haven't done the exact computations yet. But a typical X-class flare, such as the one that's shown here in the middle, that produces that image on the right, which has a saturation of up to 30,000 ADUs in our images. So it can get really bright and very geometric. So we can mask them easily, but it comes with an area loss, right? One thing we spent a couple of days on was to figure out where exactly do the X-rays come through. So you see here on the left, our sun shield with the three solar modules, and in between there are gaps that are about 40 millimeters wide. And in these gaps, you have these wires running, and this wire pattern never repeats anywhere in the sun shield. It's very unique. So I could match that to this X-ray exposure. You see the red lines here and everything else, and you can put them on top of each other, and it lines up perfectly. In this exposure, we knew the X-rays are coming in right here. So maybe we can even build an automated model of this. So on average, during solar maximum, we predict that we lose about 2% area because of this. 5 minutes only, but we need to hurry up. It's particularly bad because these X-ray flares can last hours. If that happens during one of our monthly calibration blocks, we lose these calibrations. And we had to adjust our data processing software to account for this, to detect these things. Last thing, we had water ice contamination. Initially, we thought we were fine. What you see here is flux measurements we do directly in the raw data, completely uncalibrated. We do that for every exposure. And you see like red, medium, and blue Gaia sources. So those are Gaia colors. And one step on the y-axis is about 10% or 0.1 magnitude. So initially we thought we were fine. Turns out we were not fine. So this is a baseline of about half a year approximately. So we lost about 15% of flux, and it sort of stabilized. We concluded it is ice. We didn't want to bring the entire telescope back up to room temperature because that would be a massive thermal disturbance, and we would need to recalibrate everything. So we figured out it must be one of the mirrors that is the coldest. And we see this fluxes only in vis, not in the infrared camera. So we pretty much knew very well which mirror it was. And then we warmed up that mirror from 125 Kelvin to 160 Kelvin. So it's still cryogenic. And sure enough, that worked. We recovered the flux. It was amazing. We thought, well, we understand really everything super well. We are the best. And then this... we call it the ice age. Every day we could see our photons disappearing from the camera on a daily basis. Is it stabilizing? Is it stabilizing? No, it got worse and worse and faster and faster. And we have about a 30% margin in terms of flux loss. So we can still meet our cosmological goals, but we fell through that border like very quickly. So we did something very minimally invasive and put a sort of stable telescope into a very terrible state. And then at that point, we had to do the same thing again because we're not producing usable data anymore. What happened? We've been rock stable since. No one understands what happened. There are many theories about this. We'll probably be able to recover the data photometrically. For weak lensing, I'm not so sure about this. We need to figure this out. So during the rest of my talk, to come back to photometry, I will focus on the last 4 or 5 months, where we have really excellent stable telescope. So what you see here on the right, that's a plot that was produced only last week. It was very complicated to do. These are the photometric residuals, or the relative differences in photometry for all sources that show up more than once in all the 7,000 images that we took in that period. And our photometric requirement is shown by this dashed horizontal line. That's 1% relative photometry, and you see the median is around 0.6, and the bulk is sitting down there at 0.3, 0.4%. And this is still, we are far from having the final calibration set. This is just the calibrations as we have right now, and we're doing really, really well despite all the stray light and the X-rays and so on, and the ice. In that case, no ice, hopefully. Similar for NISP, we haven't done the full experience yet, the full thing for all the 7,000 images, but that's one visit of our self-calibration field. That's 70 exposures, widely dithering. And after all calibrations, we go down to about 0.5% relative photometric accuracy. That's also pretty good. Our requirement is 1.5%. In terms of absolute photometry, I already mentioned we are using a dedicated set of white dwarf standards that are in our continuous viewing zone. For the imaging, for the spectroscopy, we're using a brighter Calspec standard. And that's one of my last slides. So the red in the left side, the red line, this is here's the beep. This is the computed 0 point from that white dwarf spectrophotometric standard, and the gray histogram is completely independent. The 0 point we determine from Gaia. So you see that these two, they line up pretty well. The width of the histogram is about 0.5% or something like this. So what that means is we are now in the position that we understand pretty well what our spectroscopy, what our path bands are, and how we need to compare that to other missions. On the right, you see this as a function of Gaia magnitude, and what you can see is that at around 19.5, there's some deviation when we compare against Gaia, and this is a schematic effect, a faint nonlinearity that is in the Gaia data. Similar for NISP, same exercise, but our data are processed by different people and they present the results in different ways. But even there for NISP, we're very stable for the last months, and also we get very consistent photometric calibration. Same for spectroscopy. And that's my last slide. I would like to point out our first data release. That's 50 square degrees. We will get them within the next 2 weeks, probably, and you will have access to them in March 25. Thanks a lot.
Perspective.
Oh, that was lovely talk, and thanks for showing all those gory details.
You're welcome.
makes me feel better about. But the question that I had was about, so you've got one visible broadband, not as broad as Gaia, and you're top of the atmosphere already, but to do the cosmology, we have to go above the galaxy. And what are the plans for reddening correction? Because the broader the band, the more nonlinear and the more difficult the reddening corrections are.
Euclid is not just what I'm showing here. We also have a lot of ground-based surveys pulled in, Hypersupreme Com, LSST, DES, JPAS, and so on, because we need very accurate photometric redshifts. about the, you're referring to galactic extinction correction, right?
Yeah.
So I don't have an answer for you. I would need to talk to our OLE photo C people, what they have implemented. But I mean, there are the Planck dust maps. There's the DESI spectroscopy, for example, that, yeah,
Okay.
I'm not in a position to give you a confident answer, I'm sorry. But yeah, it's definitely something that we have to take into account. Yeah.
Anyone else? Susanna?
There are no questions online.
What, early coffee break?
Oh, there's been a change of plans.
Huh? Change of plans.
You have to be very flexible. So Eric is going to give his talk remotely. We're done with.
Anyway.
So if there are no
One
questions.
more, there's one more.
So you showed that you're getting the same, fluxes as Gaia.
Yes.
Is that independent, or is that also circles back at some point to CalSpec or the white dwarfs from Hubble?
Gaia is what's Gaia calibrated against?
We have a hand.
I don't
So he answered that question.
Okay.
Allow me to answer this question because I work in the Gaia photometry, and it's calibrated against an own calibration set, but this itself is calibrated against the CalSpec pillars, so it goes back to CalSpec in the end.
Then it's still independent because that white dwarf, even though it was observed as sort of independent.
CalSpec.
Yeah, you're right.
I'm trying to find out is
You're right.
for the independence, right?
No, you're right. Yeah.
Okay, you would introduce the other.
All right. Thank our speaker. All right. Bear with us a minute. Figure out what we're doing.
So Eric, in theory, Eric is going to share his slides.
Can you all hear me?
Showing up.
Yes.
But no, Eric, I can see your slides, but nobody else can.
Yeah, Webex, we can see them. I can see them. on Webex.
I have to share.
Oh, no, I think you should be able, if you share screen now, you should have it.
If not, I can bring it up. Where does the screen sharing happen?
Is he doing it?
Yes, he should be.
Yes, it's sharing on Webex. You can see.
Is Kevin not here? The fearless AV leader not with us? Can you figure out how to do it? Oh.
I can see it from right here. Beautiful Nancy Grace Roman opening screen, but I don't see it.
Well, if everybody made the adjustment to the smaller screen, we can just hold this one up.
Hey, Eric, can you hear me online?
Oh, I can, yeah.
Can you turn on your camera? If you don't mind. And then if you have the slides, we recommend you share them from your end. We have them here as backup.
Okay, yeah, I'm sharing now. Are they not on the screens there?
It shows up here and it shows up there, but not.
He's showing.
You are sharing screen, you said?
Yeah, Kevin, check right here.
I was.
Or, okay.
He's not sharing anymore.
Go ahead and do it again.
What about now?
See it on here.
I know.
The Windows question.
Showing up on the WebEx.
No, back soon.
I suppose you could share the screen there and I could just say when to advance. this.
One second.
Not a bad idea. Let's break now, fix this. Yeah, let's do that.
Yeah.
So what time is it now? It is
10:20.
So is everybody okay with coming back from coffee break 5 minutes early?
Yep.
So at 10:55, a slightly shorter coffee break?
Thanks for.
45.
Thanks for difference.
10:45, perfect. That gives everybody time to check out all 5 posters. 5 posters today. All right, let's do that. Thank you all for rolling with us.
Your pie chart of time.
Very good. I need to copy.
It's Roman and
Sounds like all strong.
This term is battery power. He said you can't find
The single point of failure of the house mechanism. Why?
Well, to be all strong. Yeah, right. I'm in the military. I might put him down and ask my other question.
Yeah.
How long is the light source going to be?
Oh, yeah. NEOS.
Right. Maybe it's just like at the top. Turn it on.
There's a calibration.
Anyway, this is my chance to go.
Okay.
I don't think most people have it.
Yeah. Yeah.
Yeah.
Can you give me the, because I've gotten very into NEOs lately.
Yeah, so it's like a 4.6, 8 micron.
See, how's it going? Awesome. See you.
Narrow.
Sean. Nice to meet you.
Submit them this morning.
Asking about NEOs.
On the Flux folder? I should have already. As long as it was after 8 o'clock. 8 or before 8 o'clock.
This is a space-based?
Okay.
Yeah. It launched or?
Okay, we're gonna launch it. We're putting it together. Pieces are coming together right now. Cutting metal, going through the mission systems is going on right now.
Wow. So, and what's the one would you hope that?
27, September 27th.
So wait, so how big a field of view?
It's 1.7 by 7 degrees.
Wow.
Yeah, well, the idea is it's gotta really map.
Yeah.
We're gonna map like plus or minus 40 latitude.
That's really cool.
Yeah, and it's at L1.
Okay.
It's L1, you can see and L1's got a gigantic sun field. The idea is that you want to be able to go to. So this is, the difference here is we had 40 degrees of sun facing, so.
Wow.
Yeah.
Okay, that sounds serious.
We'll split out into the straight light, that's a.
And then you're just, it's just imaging and find how things are moving? Okay.
From here, every patch in the survey field
echo
gets
itself.
observed 4 times over 8 hours.
We'll be able to see
2-hour cases.
Yeah.
And then we go back.
Yep.
Same patches.
That'll pop up. Now we'll.
Thanks, Stefano. And so what depth do you get to? How's it going, Stefano?
You know, we're gonna be like limited in a lot of places, so.
See you.
It's gonna get down to like, 15, 16 in like Vegas systems, so it's what, like 8, deeper than maybe, so.
So they are later.
Hey,
I don't know that we actually ever met him. Maybe, to be honest.
If it was.
Yeah, so.
Yeah, well, it might have been around 2014, 2015, but I don't actually remember.
Yeah, well, the last time I gave a talk
But then
this calibration
when we
day in 2014.
Well, I'll come in and I'll just put.
That was when I was still on sabbatical.
Have them open already, that way.
Sabbatical ended towards the end of 2014.
And then there's been a couple of things, but those all go by.
All right, well, it's good to see you. Or maybe to meet you, I'm not sure which word applies. But
either way works. I mean, certainly we've talked enough. I need some coffee though.
Yeah, go ahead. I find the organizers because I'm supposed to be doing something today.
Exciting.
Yeah, no, so anyways,
Yeah.
it's gonna be a really interesting mission for astronomy.
What's the name of this? And so like compared to like LSST screen, so it's a big way.
So I am told that.
Calibration,
Fighting various things.
we have to break around noon. I mean, I think we'll make it to noon 15.
Yeah, but I don't know exactly how these things work on this. It's not on schedule.
No, so the way she had organized it, we have group photo, she wanted to have the discussion like at noon.
Yeah, that's what.
And I have a feeling we're gonna go late.
Yes, that's fine, but the question to me is different, is how we're gonna.
I don't know.
What's gonna.
I'm not in charge.
No, I know, but you are involved.
I am involved. I said, yeah, sure.
So,
I
both you and I.
know.
Hey Eric, can you hear me?
So we should find
I
out.
can hear you,
We should
yeah.
find out.
Great. Can you share your screen for me, please?
Sounds
I
good.
gotta get this. Maybe you can find out Lisa and ask her.
I didn't see her, but yeah, I'm looking
She's
for her.
probably in the cafeteria.
I tried.
All right, Darcy,
How does that look? Is
thank
it
you for
working
doing
now?
that. Yes, it is.
Okay, great. Well, thanks for improvising today.
Of course. Sorry about that.
Okay, so we'll be back at 10:45. Eric,
All right, sounds good. I'll be here.
just leave your thing shared and so we don't have to go through this again.
See the last screen, please? No.
No, he's the first speaker for the next session.
Eric is?
Yeah. And we're starting a little early at
Running
10:45.
behind.
Well, we were ahead and now we're.
Okay. So then all right, so Misha's still up next after Eric.
No, Misha's already,
Oh, Misha has gone.
Misha has already gone,
Okay.
so we have Eric.
And then we'll follow back down to this.
Yes.
Okay, cool. All right, well, in that case, let me go ahead and just get all of these ones back into their folder.
Okay, Eric, thanks for your patience and, wait, did you stop sharing?
No, I just,
You
it's
did.
sharing. Yep.
Okay. Thank you. Thank you.
Thank you.
Thanks,
See you,
Eric.
Eric.
See you in a bit.
Appreciate your patience.
Step has gotten so many people.
God, it's not with me.
As we're seeing, the room isn't even full, of course.
Yeah, no,
Let's go.
at one point I was trying to hire
Yeah.
like I know, I'm looking for.
Yeah, exactly. So,
You are? Yes.
yes, wanted to check the slides were updated.
You are
Yeah, that one.
Urban? Yeah, I did get the new updated one, I think, so.
Okay, let me.
Please, go ahead. Oh, okay.
Oh, that does not look like.
Nope.
There are a couple
The
of.
slides. Yes.
Sorry.
There, it's so good. Trying to fix it, yes.
It was named the same thing.
Okay.
Is it really in the front or almost in the front? People saved their spot.
This is the old one, I believe.
Yeah, there it is. Great, thank you so much.
You're welcome. So let's do that. We'll take today 10:30, today at 10:07. Okay, cool. So we'll do this one. This is the old one, right? Yes. We'll delete the old one. Okay.
Posters were small.
And yours is there. Make sure that's still the right one.
Thank you for double checking.
Looks right.
No, Well,
Oh, my
sorry.
It's okay.
Good thing that's why you double check.
This is the right one.
Yes.
Okay. For some reason, it didn't get moved to the. Save that. Save it to the desktop. Let's just say update.
Wait, that one's. No, that one's the old one.
The old one?
Yeah.
Where'd that one go?
The other one, you just had the window.
Mm-hmm.
It was minimized.
This one's it.
Yes.
I know I have to do the same thing. All right, so this one
Yes.
is right
Wait.
or wrong.
No,
Wrong.
that's the old one.
This one,
That one's correct.
this one's correct. This is the culprit that we need to get rid of. Okay. And one more time. Double check.
Yep.
Yahtzee.
Okay.
All right.
Thank you so
Then we
much.
get
I
it
really
eventually.
appreciate
Of course.
it.
And was he able to have it show you your
Presenter notes.
presenter notes?
I don't want to share it yet because he's sharing. And I don't want to take over. So we'll wait until that. Yep. So you are after.
I should be after.
Okay. So I'll come down once he's finished up and here we go.
Thank you.
What's up?
Dario, we're not seeing his poster.
Yeah, that was one of the ones I got updated like yesterday.
Oh, yeah,
Evening,
it's not,
I think.
it's
So
not on the screen, and one poster is.
yeah, there was a few that came in super late that I wasn't able to get to. So I have to go and download it through the iPad.